everyone, welcome to the lecture number 15 of the NPTEL lecture series on charging infrastructure, and in this lecture we will continue our discussion on closed loop control of single phase boost PFC converter. And now if we recall our previous discussion, we have come to conclusion that the two things which is necessary this closed loop control must do. First is obviously it must regulate the output voltage of PFC converter. Along with that, in doing so the converter must be operated in such a manner that unity power factor current is drawn from the source. So, with this two control objective we have defined the closed loop control, where we have one outer loop, or you can say outer voltage loop, and we have an inner current loop, and with this we are able to do the average current control. That means we are actually controlling the average value of the inductor current. It is varying in the manner of this kind of fashion. The average value of the inductor current is varying in this way. If we make sure the average variation of the current is varying in this way, then definitely we have the unity power factor current drawn from the source. Obviously it will have the ripples, so that corresponds to the harmonics in this the current waveform. That we will discuss some concept of that in subsequent lectures, but however in this lecture we are dealing with closed loop control. Let us move ahead with our discussion. So in order to understand the controller parameter, we must derive the GI of S, which is nothing but IL of S by D of S, and the GV of S, which is nothing but V naught of S divided by IL of S, which is nothing but Vc of S divided by IL of S. So while deriving this GIF of S, that means whenever there is a change in the duty ratio of the switches S1 and then correspondingly S2, then how the inductor current will respond to the change in the duty ratio, that particular information need to be found out, and that particular thing, the dynamics of that is actually captured in this GI of S. In order to obtain the small signal model, we have first defined the average large signal model using state space representation for this converter, and we obtain the the A matrix, B matrix, C matrix. Here our IL and Vc are or the current through the inductor and voltage across the capacitor as our state variable, while modulus Vs along with the duty ratio is our input variable we have. And if we see, while doing the average model, we have calculated the state space representation during the DTS period and during 1 minus DTS period. So that particular thing will give us that during DTS period our A1 matrix is shown over here. Our A matrix, which is denoted by A1, which is 0 0 0 minus 1 by RLC, and the A2 matrix, which is during the 1 minus DTS period, is mentioned as 0 1 1 minus L, 1 minus C, and minus 1 by RLC, while the B matrix in both the DTS period and 1 minus DTS period are same, which is nothing but 1 by L 0, and the C matrix are also same, which is 0 1, and the D matrix, D1 and D2 matrix are actually 0. So that is why we can also write here D1 equal to D2 is equals to 0. So these are the A1, B1, C1, D1, A2, B2, C2, D2 matrices during DTS and 1 minus DTS period. This we can do averaging over the switching period to obtain the ABCD matrices for the large signal model. Now let us try to find a small signal model out of this, which will obtain by giving the small perturbations to the input variables. So let us move ahead and see what are those perturbations and how it looks like. So first perturbation is our duty ratio. Obviously we are changing the duty ratio. So the D value is given a perturbation, that means the D value becomes D plus D tilde, which we define this as a small variation in the duty ratio D around the operating point. So our operating point is the capital D, and we have given a very small variation in that capital D, and since the variation is very small, it is also called a small signal model. So we are, and here we can define the condition that this capital D or small d is very much smaller than the magnitude of that variation is very much smaller than the operating point. and similar. So this we give the perturbation in the duty ratio. Now if there is a perturbation in the duty ratio, there is a perturbation in the current IL because of that, because since the if we give the perturbation in a duty ratio, the switches turn on and turn off time changes. Because this switches turn on time changes, the average voltage applied at the output of the half bridge, which is nothing but V converter, will vary, and if the average value of this voltage varies, there will be some change in the IL current. Obviously it has some dynamics, but there will be change in that IL current, and because of this change in the current, there is a change in the IC current as well, which actually boils down to there is a change in the voltage across the capacitor. So since we have given the perturbation in duty ratio, the IL becomes IL plus a small variation in IL. Again here the same condition, the tilde IL is very much smaller than the steady state point of IL, and then we have the capacitor voltage, which is Vc, which is again Vc plus Vc tilde, and that we can say Vc tilde is very much smaller than Vc. These are the condition for which we have considered, because since we are trying to derive the small signal model, we are giving a very small perturbation or very small changes in the steady state values which this converter have, and because since these things are there, we can also give a perturbation in input modulus Vs, which is nothing but coming as a Vd. So which is nothing but modulus Vs plus modulus small variation in Vs, and that we can say that modulus Vs is very much smaller than Vs. So these are the small perturbation which we will give in the average large signal model, and then after that we will linearize it to obtain the differential based equation, and then we can easily convert it into the S domain, linearized differential equation, and that we can easily convert into the S domain or the frequency domain, and that will give us the transfer function. So now let us see how our state space representation looks with these perturbations. So first let us see X matrix. Our X matrix is nothing but, we know that our X matrix is nothing but IL and Vc, and because of this small perturbation, our X matrix becomes X plus small x tilde. That will be our new X matrix, which we will equate this matrix into our average large signal model we have taken. So then if we see our this particular expression was nothing but, this is x dot, this is x, this is modulus Vs, one of the input, this is C is given, this is again x. So again we know our A is nothing but, we can also write A is nothing but A1D plus A2 1 minus D, that we can do because that is what averaging we have done. Similarly we can write down the B as B1D plus B2 1 minus D, and C as C1D plus C2 1 minus D. Since we are doing the average, that we have already derived in the previous lecture. So let us try to write down this particular expression. So we can do a simple thing. So we can write down this one x dot. So we can write x plus d by dt. Again in the this term we can do it, and then is A1. Since A1D it was there, so now the D is changed to D plus D tilde. So we have to write D plus D tilde plus A2 1 minus D tilde. This is again S plus X tilde plus, in the B term also we can write the same thing, B1 D plus D tilde plus B2 1 minus D tilde times modulus Vs, and that also we can write small tilde. That we can write the big, this that state equation we can write in this particular manner, because we have given a small perturbation. So, every quantity we are just giving that, we are writing that particular small quantities. So, since these things are changing, the effect of these things are, obviously we have our V naught value changes to V naught plus V naught tilde, and here we can say that V naught tilde is very much smaller than V naught. That particular thing is the outcome of this. So, we can write down, so V naught plus V naught tilde is nothing but equal to C1 d plus d tilde plus C2 1 minus d tilde, and then this will be x plus x tilde. This is what we will get as the output expression by putting this particular expression. Now, since we have already assumed these conditions, so since this d small d tilde is very much smaller than the operating point capital D, similarly this small IL tilde is very much smaller than the operating point IL, and capacitor voltage, the change in the capacitor voltage is very much smaller than Vc, actual steady state capacitor voltage, and modulus Vs tilde is very much smaller than modulus Vs, which is a operating point or the steady state point, and output change means the small change in the output voltage is very much smaller than V naught. So, we can say that since these are small quantities, all these are small quantity, these particular things are small quantity. So, the product of two small quantity will also be equal to 0. That particular assumption we can take. It is because if there are two small quantities, then the product of those two small quantities will be smaller than those two quantities. In our case, since the perturbations are very small, so the product of two perturbations becomes very small, which we can approximate it to 0. So, we can write down that wherever there is a product of Vs tilde and d tilde, it is equal to 0, and wherever there is product between x tilde and d tilde, it is equal to 0. And since this indicates very small quantities as compared to the operating point. So, since this approximation, these are the approximation we have taken, this approximation we will apply in these two expression. Let us define this as equation number 1 and equation number 2, and then try to obtain the expression accordingly. So, let us from equation number 1, let us write down this particular thing, dx by dt plus small tilde by dt is nothing but we can write a1d plus a2 1 minus d x plus a1d plus a2 1 minus d x tilde, plus we can write this expression we have written. Now, we can write this particular expression. So, which is nothing but we can write down this as b1d plus b2 1 minus d modulus Vs plus b1d plus b2 1 minus d Vs tilde, and then along with this there is one more terms which will be there, plus we have a1 minus a2 x plus b1 minus b2 modulus Vs d tilde. Now this I can write this one as Ax plus Ax tilde plus B modulus Vs plus B modulus Vs tilde plus A1 minus A2x plus B1 minus B2 Vs to d tilde, and this we can write on dx by dt plus dx small dx tilde by dt. Similarly, we can also in the previous slide equation number 2 we can actually convert it into V naught tilde is nothing but Cx plus Cx tilde times, so this will become Cxx and Cx x tilde that we have achieved plus this C1 minus C2 d tilde C2, and this C1 minus C2 and this x is there because this d tilde x tilde will get cancelled out, this product will get cancelled out. So using that approximation we can get to d tilde. Here again we have already assumed that our modulus Vs tilde d tilde is equals to 0 and our x tilde d tilde is equals to 0 since they are very small quantities. So that approximation we have already taken into consideration. Now this, let us define this as equation number 3 and let us define this as equation number 4. Now using these two expression from equation 3 and 4 we can now separate the steady state terms and the small signal terms. You can see that this x, the capital X, the capital modulus Vs, similarly a capital V, capital X terms and modulus Vs terms, capital modulus Vs terms are the terms who are actually the steady state points or the operating point around which that small signal has been given. So let us separate out the steady state terms and the small signal terms. So let us separate the steady state terms first. Now the steady state terms are dx by dt is nothing but plus b modulus Vs, because this is again a small signal term, this is again a small signal term. So these two terms are the steady state terms which we are separating. This is one expression. Similarly V naught will be our Cx and these two are the small signal terms. So now in this particular condition we know that the steady state terms are the operating points and those operating points are not changing, or small variation which we are given is of a frequency very much higher than the frequency with which the operating point or the steady state point changes. So thus we can assume that the steady state terms are not changing in the time period during which that small perturbation is been changing. So that is what the time period for that small perturbations are very much smaller as compared to the time period during which that steady state terms are changing. So thus we can very well approximate that the dx of dt is nothing but 0 because our steady state terms which are x is nothing but inductor current and capacitor voltage are not even changing during the time period of that small perturbations. So then only we can take that approximations what we are taking. So we can define the dx by dt is equals to 0. That is when we can write down that our x term from this expression, this is 0. So x term we can write down that minus A inverse B modulus Vs, that we can write. Since we assume that, or the small signal perturbation what we are giving, small perturbation what we are giving, the frequency of that perturbation is very much higher than the variation of steady state point or the operating point. That is when we can say that during the time period when that small perturbation is changing, the steady state terms are kind of constant and that's when we can make sure this dx by dt is equals to 0. So this is nothing but x is nothing but equal to becomes minus A inverse B modulus Vs, and V naught from this expression we can write V naught is nothing but minus C A inverse B modulus Vs. Just x term, we are putting this x term over in that particular, in this particular equation. Using these two expression we can easily calculate the x term and V naught term for the steady state condition. Now let us see. So these two terms indicates that the A matrix must be an invertible matrix. And from, I mean, if you recall, our A matrix is nothing but A equal to, let me write down what is the A matrix. What we have, A matrix is nothing but 0 minus 1 minus d by L, 1 minus d by C, and minus 1 by RLC. So what will be my A inverse matrix? If we see from here, the A inverse matrix is nothing but, these two get multiplied, d square by LC, and this will become, so here our minus 1 by RLC will come, this two term minus 1 by RLC, and this will be minus of B, which is nothing but 1 minus d by L, and it will be minus 1 by d by C, and then you have a 0 here. So that is what we get, A minus V minus this one we are getting, and that is nothing but your inverse of A we are getting. Now this is my inverse matrix, what we got, A inverse matrix, and this A inverse matrix we have to multiply this B and modulus Vs matrix. We know our B matrix is nothing but 1 by L and 0. Our S matrix is nothing but IL, VC, and modulus Vs is the modulus Vs. Similarly, C matrix is nothing but 0 and 1. So let us try to write down that particular x term. So x term is nothing but minus of A inverse, which is 1 minus d square by LC, and this is within the bracket minus 1 by RLC, 1 minus d by L, minus 1 minus d by C, and we have 0 here. This is the minus A inverse we have written, times B. So this will be nothing but 1 by L, 0, and that will be nothing but modulus Vs multiplied by modulus Vs. So this we can do a simple matrix multiplication. So this will actually give you minus 1 by d square by LC. This will become minus RLCL get multiplied plus 0. So this is 2 by 2, this is 2 cross 1, so the result will again be 2 cross 1, and this will become minus 1 by d LC, and this is nothing but equal to modulus Vs. Now this is the x term we have got. So again we can write down this term is nothing but IL VC. We can just open this particular term. What we will get is modulus Vs by RL times 1 minus d square, because this LC get cancel out, and VC will be modulus Vs by 1 minus d. This is the thing we will get. And similarly we can also get the, let us define this matrix what we got as 5. Similarly we can also get V naught from this particular expression. We can get the V naught from the V naught value term. What we get is V naught is nothing but 0 1 multiplied by, if you look very carefully, this is x. So x we have already derived here in equation number 5, so we can directly write that matrix modulus Vs RL 1 minus d square modulus Vs by 1 minus d, and this actually gives V naught is nothing but modulus B by 1 minus d. Now this is the same term we have derived while deriving our duty ratio, that we have derived for the entire line cycle, but at every switching period, if we assume in any of the switching period it's a duty ratio capital D, so our V naught and modulus Vs, when modulus Vs is the input, is linked in the V naught is equals to modulus Vs by 1 minus D. So this is what we have got, that is nothing but the steady state. These are the steady state terms when we evaluate these steady state terms. Now let us see what are the small signal terms, and because using that small signal term we can actually obtain the differential linearized differential equation, and that differential equation we can then take it into the S domain. So let us see that in the next slide. So similarly the small signal terms, since we are separating out the steady state terms and small signal terms from the equation number 3 and 4. So let us try to separate out a small signal term. So we will get dx delta t is nothing but ax tilde plus b modulus vs tilde plus a1 minus a2x plus b1 minus b2 modulus Vs times d tilde, and we can also get V naught tilde is nothing but Cx tilde plus C1 minus C2 x times d tilde. So these are the small signal terms, and let us try to evaluate this term, how we will get this term as we are going ahead. So let us try to write down this small signal term. Let us first write the state equation, then we will see the output equation. So we can write down the state equation, open up this state equation, dl by dt and d vc by dt. So we already know our a terms is nothing but 0 1 minus d by l and 1 minus d by c minus 1 by RLC, nothing but then multiplied by IL tilde VC tilde plus B term nothing but 1 by L0 is modulus Vs tilde plus this particular expression we have to write. So we can write down this particular big expression A1 and A2. Our A1 value is 0 0 0 minus 1 by RLC minus A2 term is 0 minus 1 by L 1 by C minus 1 by RLC. This is A1 minus A2 and this is X. So this particular, this one, I'll take one more bracket, multiplied by X. So X, capital X, we have already derived in equation number 5. So that we can directly write down, because this is nothing but equal to X. So this we can write down modulus Vs by RL Vc by RL 1 minus d square, and this one, the second term will be modulus Vs 1 minus d term. If you recall, B1 is nothing but 1 by L by 0, and B2 is also 1 by L and 0. So B1 minus B2 is 0. So this term is completely 0, and that is when this is multiplied by d tilde. So let us try to solve this particular part. So we will get 0 minus 1 by d L 1 by d C minus 1 by RLC IL tilde VC tilde plus 1 by L 0 modulus Vs tilde plus, if we equate these two expressions, this will become 0, this will become minus 1 by C, this will become plus 1 by L, and then if we try to do this particular mathematics, we can easily get modulus Vs by 1 minus d times L, and only second term you will get, which is nothing but minus modulus of Vs, because it is 1 by C, divided by RL of C minus 1 by d square, and that is nothing but d tilde, that we can get. So, and similarly this we can write down dl tilde by dt dvc tilde by dt, and similarly this v naught also we can write down v naught tilde is nothing but 0 1 x tilde il tilde vc tilde, this is again these are all vc's, plus c1 minus c2 is 0 1, so 0 1 it is, you can say that 0 0 and x il vc and d tilde. So if we try to see what we are getting here, we are getting this particular term is nothing but we can write dx tilde by dt. This particular matrix is nothing but A matrix. This particular matrix is nothing but X tilde matrix. This particular matrix is nothing but B matrix. This is nothing but modulus Vs tilde. And this particular matrix, let us define this particular matrix nothing but K matrix, and this is nothing but our D tilde which we are getting. Similarly, in the output expression, this nothing but C matrix, this is again X matrix, I mean X tilde matrix. This we define, let us define this as a Q matrix, and again this particular thing is again X matrix and then D tilde matrix. This is X tilde matrix and this is D tilde matrix, and we know that X tilde matrix and D tilde matrix, so this we have written it down wrongly. This has to be like this, and this will be nothing but X. Okay, so this particular thing is X, this particular thing is D tilde we are getting. So what we get is, we get expression, we can write down that expression is nothing but, if we try to write down this expression in the next slide, so it is dx tilde by dt thing but ax tilde plus b modulus vs tilde plus k d tilde we are getting, and the other term we can get it as v naught tilde c x tilde plus q x d tilde, that we can write down from these two expression and defining the matrices accordingly. Now if we see in this one, this particular thing we got it by linearizing. Now how I can say I have already linearized it? I have linearized it because we have considered this particular condition, that because the product of two small quantities we have considered equal to 0. It is because both the quantities are small, so the product of two small quantities are much smaller, which can be nearly approximated to 0. And this particular approximation is the one which will actually help you to linearize linearize the state equations in the presence of small perturbations. So in the presence of this perturbation, we are taking this approximation, and that particular approximation will actually give you the linearized model, and this is the one which will be actually helping out in linearizing the model. So giving a small perturbation and then taking this thing will actually give us the linearized differential equation, and that we can easily take it to the S domain. And while doing so, we have already derived this particular expression, and this is nothing but all the terms, there is no multiplication of two small varying term. So thus this differential equation and this output equations are the linearized version of the average large signal model. Now let us try to take this thing into the S domain and try to derive the transfer function. So let us take the expressions and let us define this as equation number 6 and equation number 7. Now apply Laplace transform in equation number 6. If we do that, then what we are going to get is S. Let us define this is x tilde of S is nothing but equal to a x tilde x plus b tilde of S plus k d tilde of S, we can say. Then we can define this particular, this is we get equation number 6, and we can rearrange this expression, and from here we can get Si minus a x tilde of S. This is again we have to define this capital X tilde. So this is Si minus a x tilde of S is nothing but b modulus Vs tilde of S plus k d tilde of S, that we can write from this expression. Similarly, we can also write from equation 7, we can write down as V naught of S is nothing but C x tilde of S plus Q x is the steady state terms time d tilde of S, we can write down. This term is 0, as if you see the Q matrix is 0 here, so this term is 0, so we can just have V naught of S is nothing but C x naught of S. So that means we can write down that from equation number 8 and 9. So we can write from equation number 8, we can easily write that x tilde of S divided by d tilde of S, whenever there is no change in the input variation, tilde of S equal to modulus equal to 0. We assume that there is no change in the input voltage, only there is a change in the duty ratio. So that will give us the term nothing but Si minus A inverse times K. Now let us just define as a equation number 10. Similarly, from equation 9, we can take that modulus of Vs with respect to delta of S, considering the modulus Vs of S is equals to 0, is nothing but C x tilde of S by d tilde of S, considering modulus Vs of d tilde is nothing but equal to 0. We can write down from equation 9, and this is equation 11, and we can equate the equation number 10 in equation number 11, and we can able to get the expression which is nothing but substitute equation 11 in equation 10. That will actually give you the thing which is V naught of S with respect to d of S, change in the d of S, whenever there is no change in the input voltage, is nothing but equal to Si minus A inverse C times Si minus A inverse times K. From this incorporated this value, so this we get C Si minus A inverse times K matrix. And similarly, one more things what we will get from here is that since we have written in equation number 10, that's x of s by d of s is nothing but whenever there is a no change in the input voltage, nothing but Si minus A inverse K. So from equation number 10 we can write, from equation number 10 we can also write that IL of S divided by D of S and VC of S by D of S, whenever there is no change in the input voltage, at that time it is nothing but equal to Si minus A inverse times K. So let us try to find what is this expression Si minus A inverse times K. So let us try to find out this in this half of this one. So let us see what will be Si minus A inverse. So what will be Si minus A inverse? We know this S00S minus A. What is our A matrix? Let us try to see what is our A matrix. This is our A matrix. So it is 0 minus 1 by D of L and 1 minus D of C and minus 1 by RL of C. This is my Si minus A, and that whole thing has to be do the inversion. That will be nothing but S 1 minus D of L minus 1 minus D of C, and this is S plus 1 by RL C. This inverse we have to taken. Now that will be nothing but 1 by S into S plus 1 by RLC. This becomes, and minus become plus, this become plus 1 by D by LC, 1 by D square by LC. This is the modulus, and that we will get S plus 1 by RLC, and this is nothing but S, and this is become minus of 1 minus D by L, and this will be become 2 and 1, become 1 minus D by C. This is my Si minus A inverse. And what is the K matrix we have got? Modulus Vs by L 1 minus D and minus modulus Vs by RLC 1 minus D square. So let me write K matrix as well, which is nothing but modulus Vs 1 minus D times L, and we'll get minus modulus Vs RLC 1 minus D square. Those things we have got, and then we have to multiply these two expression to get, and we have to do this one multiplication of these two expression, and then the first row element, I mean this is 2 cross 2 matrix, this is 2 cross 1 matrix. So finally we will get 2 cross 1 matrix, and the first row element is 1 which is equivalent to IL of S divided by D of S, and the second row term is nothing but, it is just the column matrix. So second row term is nothing but VC of S divided by D of S, which is nothing but the second row matrix. So that if you solve, which you can do at your end, which is just a simple mathematical computation, you will finally get IL of S by D of S, assuming V of S delta is equals to 0, is nothing but modulus Vs by RL 1 minus d cube times RLC S plus 2 divided by S square LC by 1 minus d square plus SL by RL 1 minus d square plus 1. And this, if you recall, this is nothing but, if you recall our first slide, we have discussed that it is nothing but our GI of S. So that we can write down nothing but our GI of S. Now this particular term, this particular entire transfer function what we are getting is nothing but GI of S, and there we have assumed that there is no change in the input voltage, or you can say that VD voltage or modulus Vs voltage is not changing, it is equal to the operating point and it is not changing. So that will give us the entire big transfer function which indicates the dynamics whenever there is a change in the duty ratio, how the inductor current will respond to it. And if you look very carefully, it has two poles, that means it is the second order term in the denominator, and it has single zero, that means the first order term in the numerator. So with this we will carry forward our discussion and try to find out GV of S, and then try to find out define some of the controllers parameters, and that is when we can able to do the closed loop control of the single phase boost PFC converter, achieving the regulated output voltage along with drawing the unity power factor current from the input AC source. Thank you. We will meet in the next lecture.